hard for me to remember all the details. It was a lot of mileage, but I hope to kind of get overview of some of the things and where they apply. Not all of this was I directly involved with, but some of them I was. So okay.
You want me to pass it, or you want to pass on the arrow?
I'll try to.
Okay.
I'll try to do it here.
Don't break my computer.
Don't break. I don't know if you heard you. Don't break his computer. So I mean, it's possible, but okay. So I'm going to kind of give a historical perspective on hydrogen technology and metal hydrides. Basically, Timmy gave one side of my background. This is a little more of my metal hydride technology, where I started at the Mountain Laboratory, which was part of the Atomic Energy Commission weapons program, and part of that was working on lithium deuteride tritide, which is the fusion part of the fusion bomb. So that's how I got started in metal hydrides for 15 years. I later went to Aerospace Corporation, worked on semiconductors, but then went into, they were looking for the Air Force, some missions that needed cryogenic refrigerators, particularly at JPL. So eventually I went to Aerojet, which was a subcontractor, and we worked on a project for JPL. That project ended. Aerojet didn't have a lot of need for me, so I started they had to do a couple other assignments. And JPL said, well, we're bringing back our spacecraft that we did a test on, so we'll hire you. I said, great. So there, I worked at JPL then, which we'll show a little bit of that. On the Oak Ridge, Tennessee, where you find out when you work for NASA, when the mission ends, you can be expendable. Although they did let me play with rocket fuel for a while. But I went to Oak Ridge, where I did some research there. We also helped advise DOE on the hydrogen energy program. That may be why they don't have one right now as much as they used to. I'm not sure it was me, but you never know. In the meantime, I was at the University of Utah for a while as a visiting professor. And starting now, 16 years ago, I started moonlighting, trying to consult on hydrides and their properties. And so that's where I am today. And as you can see, I've been trying to understand hydrides and utilize it now for pretty darn close to 60 years. You think I learned something, but point out a couple basics. Of course, hydrogen is the most common element in the universe, but the universe is very big. It's the lightest one. If you look on the Earth, it's 13% of the atoms, which is the third most abundant, but it's only 1% by weight because it weighs much. And really part of it is hydrogen interacts with everything. You know, molecular hydrogen, methane, natural gas, water, ice, which is everywhere, ammonia. So hydrogen, free hydrogen doesn't really exist very much unless you believe the stories coming out that there's geological hydrogen buried, trapped deep in the Earth's crust, below the crust. So that'll be, see if that's real enough, but that's a different story. Now, the main production method of hydrogen is steam reformation of natural gas, methane, and water to produce hydrogen. And so virtually all the commercial hydrogen comes from that source. And the attraction for hydrogen is that because it reacts with H2, you can form water, and water is a great byproduct. And it's in hydrogen and other fuels, but they have carbon and so forth. This chart shows the gravimetric capacity of lots of the fossil fuel. Here's hydrogen. It has a very high gravimetric density, but a very low volumetric density. And this X marks the ideal spot that the technology would like to go to. And you see it's very vacant. So one of the big challenges is, can you make hydrogen in a form that moves it up this way a little bit and not too far down that way? And so obviously, while hydrogen storage technology is a big part of this conference and has been part of the work on hydrogen for the last several decades. Now, production of hydrogen from natural gas from water, brown coal, and there's different methods. They've come up with a color scheme, and hydrogen that's made from black coal is called black hydrogen with a star. Nearly all the hydrogen that is available for nearly all application comes from natural gas, which is gray. Now, there's been plans, talks, demos, that it's going to be capture the carbon, and then for it'll become blue carbon or gray or so forth, or the possibility of nuclear energy if there was excess nuclear energy, which you could get pink hydrogen. All looks the same, but the golden boy, the one which that's supposed to be a gold ring, by the way, is the green method. Solar energy, wind energy that would have no carbon byproducts, CO2 or whatever, and that would provide the ideal source of energy. But that's not the way it's going to turn out, at least near term. Actually, I'm going to rotate this way. So how much hydrogen is actually being produced? If you look at global capacity, there's 137 kilotons per day. Most of it is used in captive audiences. This is an oil refinery, using it as processing, refinement, mechanical, or I'm sorry, merchant. Merchant is, of course, when you sell retail. Production from natural gas, oil, coal. Electrolysis is still very small, and again, and consumption is ammonia, the refineries making methanol as an intermediate product. So there's no showing the green hydrogen production, and that where the stymie is, how can we scale up and generate more of that at an economical value, which is the big question for the future. But I'm going to take you a little back in the past where hydrogen has been used. It's hydrogen that came from methane, but had been used in space almost from the very beginning of space programs. And in fact, it had similar uses before. So I'm going, and since a lot of my career was involved in that, I thought I would kind of illustrate that. And so refineries, ammonia, they produce that. And that technology, while interesting and is certainly significant, is outside what I'm going to cover. But here's the roles of hydrogen in space. Launch vehicles, and these are just three examples of rocket ships that use hydrogen, and power systems, both fuel cell and a different type of battery, nickel hydrogen battery, was used in space for over 20 years. There's miscellaneous things like making water. You know, you go to Mars, you try to get a drink of water, you're in a world of hurt. But you bring your own hydrogen, use the hydrogen as power, you got to have water too. So it has multiple uses. We can use it as a reference gas, and a gas gap heat switch is a technology that we used on a space mission, kind of the first time to do that, which I'll briefly mention. And of course, cryogenic cooling, the Joule-Thomson effect, which is how nearly all hydrogen is condensed into liquid hydrogen for that. But there are absorption cryocoolers, a technique for making cold temperature, where now metal hydrides have a role here, and metal hydrides have a role in several. In future ones, we're talking about hydrides have a role in nuclear technology from the beginning. I'm going to pass a little bit of time on, but they have been traditionally in the 50s and 60s. Most metal hydride work was really associated with the nuclear industry, one way, either energy or weapons technology. But first, I wanted to show hydrogen is the superpower fuel. And the term is, this is a rocket equation on the efficiency of lift. And this is the ISP, which is the square root of the burn temperature over the mass. And the larger that number is, the more lift you get per your fuel. And kerosene has a value of about 300. Solid fuels are typically around 260. That's in units of second. But hydrogen is 400 to 460 to make water. So this is the highest performing chemical reaction that you can use in launching spacecraft. And it has been used since 1963. And most rocket ships use them. These are just some examples. There's Falcon, which was Atlas, the new one, the Blue Origin, they're using hydrogen. Of course, the Apollo program, Saturn V, is the biggest one. There are a couple of exceptions. SpaceX, Mr. Musk doesn't have much of hydrogen one way or the other, but they use methane as their fuel. And there's another one, an earlier one that used methane as the rocket fuel. But many of these different ones, Ariane 5 was a European Space Agency, Soyuz, Atlas V, which was the early Apollo program. Now this is an example of the space shuttle. And I like to show that because what it had 230,000 kilograms of liquid hydrogen to lift this device, the space shuttle, off. And this is a photograph. There were 135 launches over the 20-some years of, or actually 30 years. There were 2 failures. You know, they were spectacular. They lost lives, but overall it did a lot. And there were 3. This is the solid. This is the liquid hydrogen and oxygen burn. These were solid fuel rockets that were used on initial boost for liftoff. But the thing is, this is in a limited case of doing space, you can handle, but liquid hydrogen is high-tech, very expensive, and potentially very hazardous because these are examples. This is where the space shuttle was over here. This is where another picture of the shuttle tank. But hydrogen had another role in solid rocket fuel. This is an example of solid rocket, whether it was a booster or for a missile of many kinds. Among the fuels, there's ammonium perchlorate with metal. Turns out hydride, particularly aluminum hydride, enhances the burn, increases the specific heat, specific impulse. This is a recent study or summary review. And so while aluminum hydride is the main one, magnesium, lithium, titanium were also used in the reaction either as an additive or as the fuel itself. And so there was extensive literature where you start with aluminum hydride. Usually it develops a coating because it's hazard, an oxide to minimize accidental discharge. Within when you we'll start releasing hydrogen. The alane, the ALH3, will turn into aluminum metal. And so these are researched, not so much in the community we're looking at for storage, but they are definitely relevant to the technology. Now, onboard power systems, again, involve hydrogen technology. This is the fuel cell of the alkaline or the potassium hydroxide, which was used in NASA programs for Apollo and Space Shuttle and had flown. There were PEM fuel cells, which of course we know are extensively looked at in current vehicle transportation. So you get hydrogen in. The storage was here an example. These are photographs I actually took down at Kennedy Space Center one time when I was touring. And So the Apollo mission would have 36.5 kilograms of cryogenic hydrogen to produce the energy. Shuttle would have more, almost 10 times. And of course, that byproduct was water, which was consumed by astronauts. So they would, it was a dual purpose. The other technology, which doesn't get as much play now, but are nickel hydrogen rechargeable battery systems that a lot of missions use. And this is their actually the cell. Here's an example of them set up. They have very long lives, so they're very durable. Again, it's a typical electrochemical reaction between gaseous hydrogen and nickel. The lithium-ion batteries in the 2010s were developed more efficiently, and so these have been changed out in the space station and elsewhere, but they were used for decades. So it's another role that hydride technology had with space. Beyond as a fuel or a source, hydrogen has had uses in experiments. One of them, the first mission that actually used the metal hydride, was a mission to Saturn, the Cassini mission. And one of the most interesting aspects of the mission was the atmosphere in Titan. It was anomalous to anything else in the Earth, in our solar system. And what they wanted to do, they wanted to analyze the composition of the atmosphere. And an experiment was set up with a GC mass spec analytical tool that was put on a probe called Huygens. This was a joint NASA ESA mission, and they used that as a hydrogen as a reference, but they needed to store a fair amount of hydrogen in a small interest. And what they decided to do was use an AB5 alloy, cerium-free mission metal. They had just 37 grams of alloy, but it stored 7.2 standard liters. And these are the little canisters. These were configured and built at Urgenics, company that Gary Sandrock, who was one of our organizers once upon a time. He's still alive and kicking, as far as I know. But his company made these. They worked on delivering them, and it actually worked quite well. They recorded data down until it landed when it worked, and they took spectra and then analyzed them. So hydrogen served a science role. The role that I got involved with extensively was as cryocoolers, that is, systems that would produce cold temperature. You think of space as being cold. Well, it's cold if there's nothing there. But if you have equipment, hardware, absorbing sunlight and panels, it has temperature. And to measure a lot of property, you need cool detectors, particularly to measure infrared radiation or microwave radiation. And there is a need for providing cold temperature. There was also a great, and the technique to do that is a Joule-Thomson effect. Hydrogen, if you have high pressure and temperature below 80 Kelvin and increase and decrease the pressure, you'll produce cooling by the thermodynamics of hydrogen. But you need to collect that gas, and then so that you could, quote, reuse it and cool again. Well, so this is a metal hydride that would do that, and this would be you would absorb at room temperature, let's say in a bed, nominally at an atmosphere or so, and then you would close the valve, heat it up to about 200 degrees Celsius, and then open a valve, and the hydrogen would flow out through a Joule-Thomson valve. This would be pre-cooled either by a radiator or another type of cooler, and then through the Joule-Thomson valve, and the gas that was being involved would be reabsorbed in another sorbent bed and then cycle. And so this is that kind of that loop where you would cycle the temperature of the bed and you would then do. So the first one was a offshoot of the famous U.S. Star Wars, not the movie, but the Space Defense Program initiative to do a test. And that actually flew on a space shuttle in 1996. And this is that layout where we use the lanthanum nickel tin alloy, a classic AB5, and zirconium nickel, an AB5, AB compound with heat. And what we had is a schematic pull down where the gas that went from room temperature and 100 bar would produce liquid hydrogen in the range of 75 K. That would then stop. Another valve would be closed. This valve would be open, and the hydrogen would flow from here up into a zirconium nickel material where the pressure was 1,000 times lower. That dropped the pressure. That would take this liquid hydrogen that was formed right here. When you drop that, you then form solid hydrogen at about 10 Kelvin. 10 Kelvin is the temperature that you needed, that the IR sensor needed, that would track missiles in flight. So the intent was, so this was started during the Star Wars thing. This is actually the program manager named Steve Bard here with the mock-up that was mounted on the sidewall of the space shuttle. And we have a description of a report here. Here are the hydride beds. There were actually 3 distinct hydride beds. 2 of them with the zirconium nickel. One was a high pressure bed where you count the high pressure would be the source to feed the hydrogen into the first JT. The second one would be the one that would collect that gas so that you could have a pressure drop to make liquid hydrogen. And the third one had the zirconium nickel alloy to it. So this is actual data from space when they operated it first time. So the temperature at the sensor was 70 Kelvin, pre-cooled, and then when they dropped let the gas flow, it dropped to about 25 Kelvin, and then in 85 seconds, and then they opened the second valve and it would drop to just a little over 10 K. This is that expansion. The motivation was they would sit, the concept was these satellites would sit in orbit monitoring the horizon for incoming missiles. If it was detected by the optical detectors, this system would start pre-cooling it. By the time the missile had gone through and cooled off, it couldn't be tracked visibly, it would be tracked by infrared. And infrared, long wavelength infrared sensors would be pre-cooled to this temperature. So but after 2 minutes, you only have to last a couple of minutes, because either you could direct fire or another missile to destroy it, or it was too late, it would have delivered its weapon. Luckily, it was never deployed. The Cold War ended, that Star Wars concept went away, but this was a demonstration experiment that it could have probably provided the protection in case that it was needed. But this work also suggested to a space science mission that was going to measure the cosmic microwave background radiation. Maybe you've heard of this. This was in 2006, the Nobel Prize. This is the remnant radiation from when the universe was formed 14 billion years ago. It's in the far infrared and microwave region, and they wanted to do a mapping of it. In order to do that, you had to provide low temperature. In fact, you had to provide temperatures at around 20 Kelvin and around 0.1 Kelvin. And so this is that first light. And JPL got the mission to develop the cooler system that was integrated with part of an international ESA and mission to develop and operate this. And so this was a ESA plank, and This is the actual map, one of the maps that was obtained after they put the satellite in an orbit called L2, where the L2 orbit out here, that's the sun, here's the Earth. As the Earth went around the sun, the satellite would always be facing to the dark side of the sun. So it wasn't clear. So you would then, as the Earth went around, you were mapping the dark side. So all that information would be recorded, and you needed steady, cold temperatures to do that. In order to achieve this, one of the most sophisticated cryogenic systems NASA ever built was fabricated to do this, where the key for the 20 Kelvin, they could, because it was far from Earth, they could use radiators to cool to about 75 Kelvin in space, but it couldn't get any colder than that. So using that temperature, they would have absorption cryochlorid that would go through a JT valve and cool the low frequency instrument. That would also feed cold gas to a 4-degree cryochlorid. It was a helium or refrigerator that would take them down to just a little over 4 Kelvin, which was then started a helium-3 dilution that would take down the temperature to the order of 10,000 degree K to cool these very long-wave radiations with a long-wave infrared. And so this is a schematic. These are hydride beds back here with storage volumes that were used. They would be like cylinders of a car circulating back and forth to provide that steady flow of hydrogen to cool and then collect it and to operate. So JPL developed that from scratch. We developed the material, we assembled it, we tested it. It was assembled. This is the plane satellite. Those are the actual 6 beds that we individually fabricated, tested. You know, I spent something like 6 years of my life doing this. And they launched in May of 2009. I got launched on a space shuttle, and actually it's Ariane 5, space. They launched it with a second satellite called Herschel, which was another science experiment. But they did do the message, or did the mission, and we actually were able to operate they were at ESA for 50 months, and there were some issues with degradation. They were able to compensate for the behavior. And I had the privilege of going to the German Space Control Center when the mission was over. We did some final tests on the cryochlorid, and they ran, and then I was allowed to shut them down. They shut down the cord, they shut down the rest of the satellite, and they sent it out into deep space. So that was has not been followed up with that particular kind of instrument. There's been talk about using hydrides for some other missions, but as far as I know, they haven't been implemented. But I wanted to move on a little bit to talk about hydrogen as a clean and renewable fuel and how it can be used, and to put that in perspective now, you know, clean energy really has 2 options: wind and solar. Solar can be directly powered into electric motors, batteries, and the other way is to use it to make hydrogen, one way or the other, green hydrogen, and then transport it and put it to vehicles, store it, do whatever. So there's a much more complicated infrastructure here in Pride. And as we've heard, you know, talks already at the Bowman conference, and there's reviews in the literature that talks about the challenges, but still, that's an energy carrier of using hydrogen, and hydrides have a number of potential roles in that. And so, but here's its status. Of course, fuel cell has advantages, but the battery is way ahead in numbers, way ahead in plug-in hybrids doing that. Again, part of it, the fuel cell does have technological advantages. It certainly can use greenhouse gas, but it's not necessarily as energy efficient when you take all the steps that have to be done. And so, and not as easy to implement. So optimization, development is still critical for incorporating the fuel cell technology. And part of that has to do, of course, with the volumetric density. This is one of the charts on the properties of hydrogen. And these are the targets that the DOE has set up, saying, well, you got to be able to have a volume density of that. And this is the density as a function of pressure for this is ideal gas would be up here. Real gas, because of compressibility, limits you here. And so this will barely meet the target at about 700 bar pressure, which is a lot of pressure. And of course, you have to contain it. And the way has been done now is storage tank type 4, lightweight, built to withstand structure. And but there are ways to store it. This is my favorite cartoon on hydrogen absorption, and I've shared it a lot of times. But maybe I'm prejudiced, so I like absorption, and I do like eating pies, whereas absorption is kind of messy, but it does work. You can store it, but it's kind of. But anyway, so I'll often stick it in no matter whether it's relevant or not, just so it reminds me. And again, they're reversible, non-reversible. We've talked about each method has some advantages, each has disadvantages. And it's not easy to intertwine or find one that has all of them, but still, fancy, okay. So, but again, for volume density, if you just store 1 atmosphere, it had to make it 4 times bigger to have the same quantity of gas, 150 bar or 700 bar. So obviously you need high pressure. Liquid hydrogen is, you can get it down to project temperatures. The various materials, interstitial hydrides, complex hydrides, sodium malonate, chemical storage are these sorbents and water. Water is actually very good. So you got to break those strong bonds. And first, if you're going to end up going to water, you'll lose the reaction. But I don't think that's a near-term alternative. Okay. Of course, this is the type 3 carbon, type 4, which is the most widely implemented at high pressure, are the high density. They do work. They can be handled with current infrastructure, but there are safety concerns. Plus, they take a lot of volume, and so they're being used. But many of the few demos, the ones that were constructed, had 350 to 700 bar. These were prototypes in the 2000s. Many of them were used, and some were eventually second generation were sold. But again, they're all different companies doing that. But we heard from Toyota, our speaker this morning, and of course, we know about the interstitial hydrides, just pointing out that electrochemically you can put it in by breaking up water, or you do gas phase with distillation, and it goes into the labs. And these are usually reversible in the right conditions, different types of container, different ways for managing, because the reaction in the gas phase is exothermic. You have to remove that heat to get the hydrogen to absorb. And you have to supply that heat to get it to desorb. So there's a lot of engineering, thermal management that has to be done concurrently with materials development. And that has been done. We have presentations here, we have posters where people are looking at different ways of doing that, and it has been looked at a long way. It's not an easy problem because you're balancing a lot have to try to balance very many different kind of properties, behavior. And of course, this is the famous PCT diagram where this flat region in converting phases is the ideal for absorbing or desorbing. This is data that's often plotted. This is the reality of most systems, is that they're an absorption versus desorption hysteresis. There are a slope for each of them. So when you're working in two relatively fixed points, the effective capacity is often quite a bit lower than the ideal one if you were saying, I just looked at that. So again, that's trying to find ways to minimize slope and avoid it has been part of the design exploration effort that's been done. Now, of all of the many various ones, these are hydride bed or forklifts. They were ones that were early. It seems like relatively low hanging fruit. They work in a location, you can supply hydrogen, you need mass, so the fact that you have storage tanks and so forth. And so they've been done on utility relatively early. And so this is a couple of examples of those where they replace batteries. And so you know it's certainly workable, and they've been done. Several organizations have done it. So that is a way to go. I haven't run out of time yet, but I wanted to now talk about kind of a little more history aspect of hydrogen and metal hydrides. We know, for example, metal hydrides were discovered in the 1860s by palladium mining. But hydrogen was generated as a gas and was used as early as the Civil War. In the 1860s, the people would take a balloon, fill it with hydrogen gas, and go up and use it to fly. And so it was hydrogen. Now they didn't use they used an on-site generator to gas, and they were useful, but they were also very good targets too. But they were done. Hydrogen had a role in that military time, and in World War I, the Germans also said, "Well, we can make zeppelins with a large sheet where they would make machine guns and bombs, but they would carry rain into England, and they actually did. And in 1915 and 16, there were a total of 52 raids, and it cost the lives of more than 500 people. But again, these were vulnerable, and they were abandoned in light of other things. But it was a way that hydrogen found another military use. But one other technique was for transportation. Right after World War II in the 20s, this was the airships in which the Hindenburg was one that caught fire, and it became famous or infamous. The story is that the Germans wanted to use helium, but there wasn't that much helium around. A lot of it was controlled by the United States. And so they went to hydrogen, which they could generate. And it worked for a while, but they had accidents. So it quit being used for that. But the downside publicity has haunted hydrogen technology ever since. It is hazardous, and it needs control. And pushing the envelope can get you into trouble. But they did still use hydrogen balloons far through World War II. And this is where a metal hydride was used, calcium hydride. It would react with water, so hydrolysis type reaction. And they would send weather balloons. And they were actually could be go quickly and fill up. And so these were used as another example and of collecting data by using hydrogen uh, as a lifting media. As far as I know, there weren't any people on these. They had instruments that they would record. This is a GM electro van. This was originally a battery-powered car or vehicle that in 1966, GM converted to run on an alkaline fuel cell and used hydrogen and oxygen, just like were being used in 60 for rocket ships. And so, and it was put together and it would go about 100 miles. It was a 6-passenger conventional van. Here's a cross section. Here is a liquid hydrogen tank in the back, and here's a liquid oxygen. See, not a whole. These are the fuel cells. Took a lot of space. You can put in your power supply, but not much else. And 2-passenger. But it was a demonstration by a car company that looking at an alternative fueling system. But what really changed rural hydrogen 50 years ago was this oil embargo. The oil embargo was international. It was particularly hard hit in the United States. And because of the consequences, the government, particularly what was the Atomic Energy Commission, offered out to laboratories, to university, to find some way to replace gasoline as a fuel. And hydrogen was the identified one. It became in the popular news. This is from a popular science magazine. You'll note there's a Polaroid camera here. I mean, that was state-of-the-art taking photography too in 1973. Yeah. But here's the headline about hydrogen fuel of the future. And so there was all kinds of talk. They would modify cars that run on hydrogen, internal combustion engine. They would burn hydrogen. They could do electrolysis. Airplane could be burned. So all kinds of ideas were proposed. And of course, they'd used the Apollo oxygen system, similar to what GM had done. They were talking about using catalytic hydrogen burners instead of natural gas. Get away from the bad fossil fuels. Well, where I was working in Mount Lebanon, we also got some funding. And that's when I personally got involved in looking at renewable energy. And what we were doing is looking at metal hydride, looking at roles of crystal structure, composition, phase diagram, electronic structure, how we were there, dopants, and I did early work on the titanium iron hydride, the AB5 nickel, doping those, and others, a number of others trying to do that. We collaborated with a lot of international organizations, and that by the 1990s, and about 15 years, I had personally collaborated with about 45 papers and conference proceedings on this work. When we were at Gordon conferences, I would often find my collaborators here in the audience, and we would talk about new work. Now, again, in the 80s, and it died down, but in the 90s, again, the issue came up, particularly because fuel cells were being developed, and there were further demonstrations. So with hydrides being utilized instead of gas storage, the issues with gas and liquid hydrogen, and so there were mostly utility vehicles, but there are. This is a German submarine that was developed, and that's an AB2 type storage material in a long tank. Again, connecting with the fuel cell, a hydride storage bed, the heat could go back, and so this was looked at, and going to the demonstration. The German Navy actually converted or built several submarines to run silent, and they had deployed some in both the German and Italian Navy. Again, where you the weight of the hydride is not necessarily a disadvantage, and this is another photo of that showing a hydride bit being put into place. And as far as I know, they're still in operation. I kind of asked around it and heard they're not. But there were other maritime vehicles being done in the same 20-year period. And you can't see all the examples, but all around there were cars, buses, things being done. So there's around 50 of them. This is actually from a rather new review. I highlighted the one. This is a boat that was done in England, called the Ross Barlow, which had fuel cells, and they used an AB2 type alloy, and would store. And it ran for a while. It did demonstration periods a bit, but it apparently has stopped quite a while ago. But again, there's been a lot of stop-start demos and let go. But there was a renaissance, in a sense, that started in 2002, 2003. And that was when hydrogen was going to replace fossil fuels because greenhouse gas warning was being more concerned. And we set up a large integrated program with centers of excellence. The intent was to go beyond materials discovery, but go to integration development. So we're looking at the three types of materials: hydride, chemical storage system, absorption system, and then there was an engineering system, of which several of the people here were involved with, and trying to integrate to address more. And so for almost 10 years, it was very active, and it still continued, but it did slow down. And but these are the technologies. I mean, they looked at liquid hydrogen tanks, they looked at compressed gas. There were some more demonstration. I mean, I know you can't read that, but they would look at cost trade-offs. These were issues that were needed to be done. And there were examples. There were the metal hydride. Metal hydride still had cost issues, and they were talking about using them for more than a specialized application. But there were now a list of fuel cell passenger that could be bought in limited editions. And so I pulled this reference out of Wikipedia last fall, and we actually heard from our speaker from Toyota this morning about the number that they sold, and still, again, they were small fleets being done, but still looking at ways to. And from my, applicant viewpoint, there were two that were particularly from. One is the US DOE did a hydride reserve for a thing for a forklift type device, a utility vehicle, where you needed something that would be clean, not generate gas, and not be the same as battery technology. And there was a similar program out of Germany where they put one together that they described how it was working too. There's currently a truck now by Nikola that's using compressed hydrogen again, less on the metal hydride technology. In the early 2020s, which doesn't seem that long ago, there was a bipartisan infrastructure, and it was going to, again, go back to address issues with cost and scale and control emission and with tax credit and so forth. It was just getting started as planned, and they were being planned for this year or last year and this year, and they were actually got initial funding, and they were going to have hubs to practice more, to go to the next step. Use what we had, look for maybe ways to make some better materials, but follow through. But there were a lot of senators described. You'll see question marks because all of a sudden there was a change, and that was the election of Donald Trump. And what has happened is that while not everything has been completely stopped, almost everything's been on hold. And so a lot of these cuts to the funding and there's shifts in the program now, instead of being renewable and green, said, well, can you get hydrogen from coal and use that some way? And so it's kind of, and tax credits would be eliminated. These are still working through U.S. Congress. This is, it might have changed in the last couple of days since I've been here, but I don't know that. But still, I have this question: will hydrogen vehicles actually become mainstream transportation? And I'm hopeful that it does prove to be viable in certain applications. And I think that, from my own view, I'm looking at that. I think that fleet type operation, and particularly tied to green sources of gas, where you don't have to do all the infrastructure, would be viable at this phase to go forward. Trying to make passenger vehicles go, the infrastructure is too demanding. And been said a lot of times, a classic chicken and the egg scenario where they won't make fuel cell cars because there's no place to fill them up. They won't make filling stations because there's no cars to do that. And that's not going to be easy to do, I don't think. But I think you can get improvement in storage systems, but optimization is going to be very hard. There's a lot of contradictory trade-off, and when you factor in costs, that's going to be more. And there's really no material that can meet all those storage capacity, all those parameters for storage and volume and cost and operation. So it's, again, optimizing for a particular set of operations, not for general. However, compressed gas do allow for vehicles, would allow the rest of the infrastructure to be done. Can they be made more efficiently to demonstrate fuel cell technology? I want to end with a commercial. LesDiablerets has been editing a book with us. A book on the new materials and technology for hydrogen-based energy storage. It's going to be released October the 1st. It has 20 chapters. I have contributed to 2 chapters. One that I'm sole author is metal hydrides and tritides. I didn't talk about those today. I figured I was going long enough that I didn't need to take you down that path too. But I do recommend it. We've worked hard to try to update what the science is, what the technology is, and what the play is. So I think it'll be a worthwhile reference for everyone. And with that, thank you for your attention. And I'm excited for the question.
Any questions, Bob? We don't have any people carrying the microphone. Just one. Wait a minute.
Here. Also, very much for your excellent lecture.